Hi, this is the lecture video for the chapter on systematic treatment of equilibrium from the 9th edition of Harris's Quantitative Chemical Analysis. In the 8th edition, this was chapter 7. Now in the 9th edition, it seems it's been moved to chapter 8, and chapter 7 is actually on titrations, which will be included in a different lecture video. The learning objectives for this chapter, however, remain the same, and they deal with relating things like activity and ionic strength to equilibrium, and then specifically dealing with the systematic treatment of equilibrium, which will be in the second video for this chapter. So let's start with solubility. Well, first we just need to consider what it is that allows something like sodium chloride to dissolve in water. And if we think about it, it is actually the polar water molecules that help to stabilize each of the different ions, the cations and the anions, as they separate from one another. And they end up being attracted to the differing polar ends of the water molecule. And so this solvation process stabilizes those ions in their ionic form rather than in their solid form and allow it to dissolve. Now remember, we talked about earlier for types of equilibrium constants, we talked about KSP, and we defined this as the solvation of an ionic compound to form its soluble ions. So if we take a look at this silver thiocyanate compound, we have a KSP that I have provided here at 1.1 times 10 to the negative 12th. And if we write a Rice table for this, we can see that that silver thiocyanate is in equilibrium with the silver ions and the thiocyanate ions, which are solubilized. We can continue to fill this Rice table out, acknowledging initially that, of course, the silver thiocyanate is a solid, and so it doesn't factor into any equilibrium expressions. We also can say if we're starting initially with the solid and adding it to water, or vice versa, we have zero concentration of the ions at the beginning, but we add some value to them after that, which is plus X. Then we add up those columns and we see that the change in those at equilibrium, or sorry, the final equilibrium expression from those is X and X. And if we write out the equilibrium expression KSP, is the concentration of each of the ions multiplied, then we can also say by substitution that KSP is equal to X squared. And we can solve for X, identifying it as 1.05 times 10 to the negative 6th. This is a basic Rice table equilibrium calculation, something that you should be well familiar with at this point. Now, the part that becomes new is when we start to consider what would happen if that same solution contained some other ions. So in this particular case, we're asking the question, what would happen if this solution of silver thiocyanate contained some, and that is 0.06 molar potassium nitrate? Would those ions have an effect on the equilibrium of our silver and our thiocyanate? And in order to consider that, we need to talk about the topic of ionic strength. And we're going to relate that to solubility here in just a moment. So at the top, we have the same KSP equilibrium. Of course, I've had to substitute in a different arrow, so forgive me for that. But we have the same equilibrium expression at the top. And the question really that we distill the previous slide down to is what happens to the attraction between our silver ion and our thiocyanate ion in the presence of potassium nitrate. Now we know that potassium nitrate, or you know now as I tell you, is a soluble salt. And so we expect it to form nearly completely potassium and nitrate. So what sort of things are going on in solution? Well, as it turns out, the attraction between the silver and the thiocyanate decreases as we add in other ions. We can think of this in sort of a visual or verbal sense here, that we have potassium ions and nitrate ions as we add them to solution that are taking some of the attention of the silver and the thiocyanate. And so we're seeing that it's stabilizing their charges, the interaction between them decreases, and as a result of that, the solubility of thiocyanate is increased because we see that they don't need to be stabilized by one another. They have other interactions going on, and so we can actually get an increased solubility of our salt of interest. So I'd like for you to try to just take a moment. If you need to review the section in Chapter 8 from Harris, feel free to do so. But I'd like for you to try to just take a moment and write a sentence or two that describe this interaction and the outcome of it in your own words. Pause the slide, take care of that, and then resume with me in just a minute. Okay, so as we move on from just the basic understanding of ionic strength, we need to, of course, have some way to quantify this. And ionic strength, which is given the Greek letter mu, is a measure of the total ion concentration in solution. And an example of this would be that we could have our silver thiocyanate solid in the 0.01 molar potassium nitrate. It's the same compounds, just different concentrations. So if we want to draw a graphical representation of this, we could see that we have the silver ion, we have the thiocyanate ion, and then we have associated with them a number of nitrate ions and potassium ions. We can see that the anions of the nitrate are grouped around the silver cation, and the thiocyanate anion is grouped with the potassium cations because those opposites are attracting one another. We also need to understand, as I'm beginning to illustrate here with this curved arrow, that this is a dynamic process, meaning that since we're in solution, each of these different ions is coming in and leaving the interaction with other ions. So in the end, a net charge for each of the two center ions, the silver and the thiocyanate in this case, never exceeds, that is the external ionic atmosphere, the sum total of all of the charges of those other species integrated over time never exceeds the charge of the central ion itself. And finally, we need to understand that the greater the ionic strength, the higher the net charge in the ionic environment. And so if the central ion has more charge to it, let's say we had zinc 2+ instead of silver 1+, we could have a stronger ionic environment around it. And if nitrate was a stronger ion, instead of a singly charged anion, maybe a doubly charged anion, it would bring with it a greater ionic strength. So we need to have a way when we actually calculate mu to account for concentrations and their charges for each of the individual ions in solution. And that's exactly what we're going to do. We have mu is equal to 1/2 the sum of all of the concentrations of each of the individual ions times each of their charges squared. Now, if you think about this, we ought to square the charges because we have positive charges and negative charges. So we need to have a consistent way of handling those so that the negative charges become positive and they all factor into the ionic strength. So this is what we're going to do it, and how we're going to do it. It includes all ions in solution. And a good example of this I can show below here. So for the ionic strength of 0.02 millimolar magnesium chloride and 0.03 millimolar aluminum chloride, we would write down the following information. We're given that magnesium has 0.02 millimolar, chloride is the sum of the millimolars from the two compounds times their molar coefficients, and the aluminum, I'm sorry, I forgot the L here, the aluminum concentration is 0.03 millimolar that we're given in the problem. So now if we fill out our equation for ionic strength, we see that mu is equal to 1/2, and now it's the sum of each of those terms where we take the concentration of each of the ions times the charge squared. And you can see then we're adding up each of those terms and then creating this product where we say that mu is equal to 0.24. So the question here then is, what about neutral compounds? So let's say I took some sugar and I dissolved it in this water. It's solubilized, clearly. We can make sugar water very easily. How do we account for that in this? And as it turns out, we don't have to account for them. We're talking about ionic strength specifically. And so the term, hopefully for you, you were maybe even rolling your eyes, but the term really tells us that we're not worried about neutral compounds. It's only ionic compounds that we have to take into account, but we need to be careful to make sure we account for all ionic compounds, because neutral compounds have no effect. All right, so let's take a look at a simple plot here out of the text. Now, the plot that we're looking at is actually representing the solubility of potassium hydrogen tartrate. So we've got that on the y-axis. We've got the concentration of added substance, each labeled on their lines, on their respective lines, on the x-axis. And so what we're taking a look at is what happens to this solubility of the potassium hydrogen tartrate as we add various amounts or increasing amounts of other compounds. Notice from the chemical formula of potassium hydrogen tartrate, it has potassium in it. So on the bottom line in the plot, we notice that there's a similar ion. Remember, we stated before from, I think, Chapter 6 in Harris, that we have a common ion effect. And so each individual ion has a maximum total solubility. And if I have another chemical species contributing to that solubility, it's going to decrease the total solubility of each of them, keeping the solubility of that particular ion between the two of them constant. On the other hand, glucose in the middle, we can reason through that this is neutral, so it should not affect. Based on neither common ion nor activity, this should not affect our solubility. Remember, these are KSPs that we're talking about. Sodium chloride does not share a common ion, but notice that sodium and chloride are both singly charged cation and anion. On the other hand, magnesium sulfate has doubly charged cation and anion. And so those doubly charged ones more appropriately or more adequately charge stabilize our potassium and our hydrogen tartrate, allowing for more increased solubility with greater charge. So if we label the plot, we can see that the middle one is molecular, so there's no change because there's no charge. The bottom one has common ion effect resulting from the decreased solubility of our species because K plus solubility remains constant. The top one is 2+ charged ions, and so we see an increase in the total solubility. And the sodium chloride is an increase in mu, but not as strong of an increase as mu for magnesium sulfate. So while we see an increase in solubility, it's significantly less. All right, so let's move on to activity. Now, activity really is getting at a term that is very similar to concentration, but in a number of ways distinctly different. So first, we need to consider the ionic strength that we've just been talking about in a way that helps us account for ion interactions in an equilibrium reaction. And so activity is a substitute for concentration. I already said that they're nearly identical. And the reason for this is that not all ions are either soluble or available for reaction at any given moment. So activity tries to take this into account. We take our concentration, C, times an activity coefficient, which is a reference value we can look up or calculate. And this value describes the deviation from ideal behavior, where activity would be equal to concentration. Now, it's important to note here that our activity coefficient ranges from 0 to 1. So we can never have an activity that is greater than the concentration. Our concentration is our theoretical limit, and that's if our activity coefficient is equal to 1 and there's no deviation from ideal behavior. Now, if there's a complete deviation from ideal behavior, we expect gamma to be 0. In that case, activity, or A, goes to 0 also. So we should expect ranges that are fractional portions of concentration for our activity of each species. So let's take a look at how mu and activity are related to one another. They are related through the equation I've provided here, the extended Debye-Huckel equation, where the log of the activity coefficient is equal to the equation I've provided here. Now, I've labeled below each of the values. So the activity coefficient gamma, Z is the charge of an ion, alpha is the size of the hydrated radius of the ion. The mu is the ionic strength, and these terms all factor into this extended Debye-Huckel equation. Now, if we take a look at this, we can see that as gamma increases, it means that deviation from ideal behavior must increase also. We already know that. So that's to allow us as gamma decreases, It means, as we just talked about, the deviation from ideal behavior It means that deviation from ideal behavior increases. We can also see that as ionic strength increases, gamma is going to get smaller, therefore deviation will increase. And as the charge of the ions increases, gamma gets smaller also, and so we'll expect deviation to increase. This is a table pulled from Harris, and what you'll notice is on the left we have charges of different groups of ions, plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4. We can find a particular ion we're looking for here, and then you'll notice on the right, each of the columns, we have the ion size in picometers, so this is our alpha term. We have our ionic strength for mu, calculated at various concentrations. So our ionic strength mu is the 0.001, 0.005, 0.01, and then the activity coefficients are what are below for each of those different concentrations. So we can look these up at predetermined concentrations that we happen to be working at and work from these activity coefficients and multiply them by our concentration to actually get our true activity. Now, you might be wondering, what do we do in between these values? So first, let's pull a couple of values from the table and make sure that we're getting the right ones. So I've identified a few ions here, and we have some different ionic strengths or concentrations in the table, and I'm just going to look at the table and I'm going to fill this in. So I want you to pause it for a moment and see if you can find these, jot them down with a pencil just in case you're doing it wrong, and you can fix them, and then we'll take a look. I did just notice that the concentration of the second column here, I must have corrected here, and so it's 0.01 instead of 0.03. But you notice that the values here I'm just pulling from the table, and hopefully you can find them fairly easily. Now these are the x values. The y values are below. And now what we're going to do is we're going to interpolate if we don't happen to be at one of these concentrations. So let's say we happen to be at a mu of 0.008. Then we're going to take two adjacent values. We're going to use the x and the y, and we're going to calculate the value that we need using what we know of the rise and the run and a straight line equation between them. So you can see here I've taken those values, I'm solving for the y value here and filled in all of my others using my concentrations, using my my ionic strengths, and using the activity coefficients that I have from the table on the left. When I do this, I'm able to solve for a y value, which is my activity coefficient for this particular this ion sulfate that I have at a concentration or an ionic strength of 0.008 molar, and I get a value of 0.692. So as ionic strength increases, the activity coefficient decreases. So another way of saying that is as mu goes to 0, gamma goes to 1. Another thing, as ion charge increases, activity coefficient decreases. So as activity is more important for ions with greater charge. Finally, the smaller the hydrated ionic size, the more activity effects are important. So keep these three things in mind as we're considering the interplay between ionic strength and activity and calculating values of these going forward. So now let's actually use what we've learned about activity to calculate something that's relevant. So as it turns out, pH meters measure the H plus ion activity and not the H plus ion concentration. We can think of this as saying that the activity is what's relevant to the meter, and all we can measure are those ions that are available to be measured, those that interact with the probe itself. We can't measure those that might be busy in interactions with other ions in solution. So what we want to do is we want to try to calculate the pH and the H plus ion concentration using what we now know about activity for a 0.05 molar lithium bromide solution at 25 degrees Celsius. So let's start with our ionic strength. Mu is equal to 1/2 the sum of Ci Zi squared. So I place in here each of the ions of each of their concentrations. And notice that for lithium bromide, each of the charges are 1. So in the version I've listed there below of the equation, 1 squared is just 1, so I didn't include it in the original. We get a gamma value for H plus and OH minus out of the table. These values are 0.86 and 0.81 respectively. And then we can write our equilibrium expression, Kw, which we know to be, we'll just say 1.0 times 10 to the negative 14th to keep it simple, times H plus times OH minus, or equals H plus times OH minus concentration. We substitute in activity, which of course is really our activity coefficient times our concentrations. Then we substitute in X because we want to be able to solve for one value. We also know that H plus and OH minus are equal to one another. So when we've done that, now we set those equal, we solve for X, and we see that X is equal to 1.2 times 10 to the negative 7th. That's the activity of H plus and OH minus. If I take the negative log of that, I end up with pH is equal to 6.92. What you'll note is that if we do a routine pH calculation from Kw and just our numeric value there without activities, of course we solve for a pH of 7. So there's a slight deviation, not a huge one, but it is probably important for us to take this into account from time to time. Finally, I just want to mention that because of what we now know about activities, we need to rewrite our equilibrium expressions. So when we write them, instead of just using concentrations, we substitute activities with the same molar coefficients raised to the exponents. And you can see then when we substitute in our concentration times our activity coefficient, each of those retain the exponent. So the expression at the top is the one that we want to use, or one like it, for each of our equilibrium expressions when we're trying to account for activity, though we will not necessarily always do that. So I want you to take a moment and write the equilibrium constant expression for the reaction we talked about earlier in the video, for silver thiocyanate and its KSP. So pause the video here for a moment and make an attempt to write that expression, then I'll write it and you can double check that you got it right. Alright, so this is a KSP. KSP is equal to the ions multiplied with their molar coefficients, which in this case are 1, which is equal to the activities times one another. We substitute in then the concentrations times the activity coefficients, and we end up with Ag plus concentration times its activity coefficient times the thiocyanate concentration times its activity coefficient. So now we're going to use this to find the molar solubility of the silver thiocyanate in a solution that contains some iron nitrate, 0.06 molar. We have our KSP here, which apparently the exponent got shortened there, and so its KSP is equal to 1.1 times 10 to the negative 12. You can write that in there. Okay, so we write in our KSP, which we already had from above. We can solve for mu. You see I do that here, where mu is equal to 1/2 times the sum of 0.06 times 1 squared plus 0.06 times 1 squared. So mu equals 0.06 molar. You can also see that we can then use that to find our values for our activity coefficients from the table, and then extrapolate if needed between the points, and we get gamma of Ag plus is equal to 0.80, gamma for our thiocyanate is equal to 0.81. We can plug those into our equilibrium expression using our numeric value for KSP and these activity coefficients. We end up with only one unknown, and that's X, and we can solve for that quite simply algebraically. We see here that X is equal to our X is equal to 1.3 times 10 to the negative 6th molar. And this is different than if we hadn't factored in our activity coefficients. Notice that we're only having about 80% activity from these ions in the presence of other ions. So they're being solubilized, but that also means that part of their time is being spent interacting with these other ions that are solubilizing them. So there's complex interactions going on. Now, we certainly will do some more example calculations like this in class, and what follows this in Chapter 8 is the systematic treatment of equilibrium, where we'll do multiple equations and multiple unknowns to solve for concentrations of unknown species in complex equilibrium situations.